Wonderful. Welcome, Collin.
Great, thank you. And thank you, Senthil. That was really a fascinating and very timely talk and a great segue for some of the things that I'll be talking about. So just to put this into some perspective and what my perspective on these issues are. So in addition to being a professor in ECS, I am a cardiologist at Massachusetts General Hospital. And my point of view on these issues is admittedly poisoned by these interactions. And this will touch on many of the things that some of the things that Senthil and Marze have spoken about. This talk, in my view, is a sort of a talk that presents my personal bias, those of my clinical colleagues in this area. So there's going to be no results from my research group here, but just so I can make a simple point. So to begin, I think starting with the same nomenclature is important. So what is clinical decision-making look like in 2021? Very simple paradigm. Patient provides information to the healthcare provider, and then the healthcare provider has to use these data to decide what actions to take, what medications to give, and what procedures to perform on that patient that's going to improve their quality of life or make them live longer. This very simple diagram in more realistic terms looks something like this. Clinician is inundated with a variety of different data in the electronic medical record. And here, this is sort of I think this is a dummy in an intensive care unit. You can see there are many different types of signals that the clinician has to process. These signals come in very different modalities. Some of them are physiologic time series data. Some of them are other data that are lab values and such. So it's disparate data, and the human mind cannot process all of this. And the promise that that clinicians have been told in this space is that there is some mystical animal called machine learning that can process all of these data to provide the clinician with summary information that he or she can use to make decisions, and with the goal of minimizing length of stay, readmission rate, complication, essentially to make informed management decisions. Now, if you look at the literature, there are many success stories. I think Marze has alluded to some of these, and there are many problems that are solved if you read the literature. So we can use machine learning to make diagnoses with medical images. We can classify arrhythmias. We can do cancer prognostics and such. But however, while I think there's no doubt that everyone recognizes the importance of machine learning in the healthcare sphere, it's not generally been embraced by the clinical community. And why is that? And as Marze said, these things can be very complicated, highly parameterized models. And here, just showing a simple deep neural network, or a schematic of a deep neural network. And these models, as has already been said, are complex, contain many modifiable parameters, and can be very hard for the layperson, in particular for the clinician, to understand. So in that vein, if you think about ML and AI more generally, and you look at the computer science literature, and in particular some of the conferences that publish in this sphere, there's a lot of enthusiasm amongst the computer scientists. Clinicians, however, the enthusiasm is generally a little bit muted, and there are unanswered questions here. And I would argue that this muted enthusiasm is warranted for a number of reasons. So the data scientist's metric of success, and I think this was one of the things that Senthil, in Senthil's very, very poignant and very, very apropos examples, that the metric of success is standard statistical measures: accuracy, discriminatory ability, sensitivity, things that every statistician it's in their lexicon. However, machine learning in healthcare, accuracy alone does not always, and I would argue, nor should it, ensure that the resulting model will gain clinical acceptance. And the reasoning has already been said. No predictive model is accurate 100% of the time. Unlike other spheres, however, wrong predictions can have disastrous consequences for the patient. So if you think in particular about risk stratification models, if there is a model that predicts a patient to be low risk when he or she truly is high risk, you've missed an opportunity to intervene and to save a life. Now, simple models that are a function of few parameters have had their day in the clinical literature. In fact, most of the models that are clinically used are based on simple logistic regression or Cox proportional hazards modeling. And in part because they're easy for the human mind to understand. the features that go into these models have clear clinical significance, and so they've been more likely to be embraced. Now, I think one of the things that, as Alec has talked about, is one of the things that our group is interested is using our understanding of pathophysiology and stuff to sort of design these deep learning models in a better place. But the overarching point is, as deep learning models do not directly leverage a prior understanding of physiology, it's very hard and difficult for the clinician to understand what a deep learning model is doing. In particular, understanding a priori when a model is likely to be misleading can be very, very challenging, especially with complex models. So to put this in summary terms, evaluating a complex model, whether it is trained on images or whether it is trained on the electronic medical record or uses those data as input, such black boxes provide little intuition in how the model arrives at a result and can be difficult for the patient to accept. And more importantly, leads to some uncertainty about whether the model is appropriate for a given patient. So when you look at the typical healthcare provider and he or she has any model that they use to for risk stratification, then there are some questions that enters the clinician's mind. So for example, even though the overall performance is determined by standard statistical measures of success is good, will it work for the specific patient in question? Moreover, is the model consistent with what is known about human disease? So a typical model is trained on some set of patients. Those sets can be problematic, especially if they're observational data sets for many of the things that Senthil has articulated. And but the first medical school, I think, was a few centuries ago. So when one presents a model to be used that has been trained on some cohort of patients, you'd like to be able to understand or put that model in the context of these several centuries of medical understanding, and is it consistent with those principles? And lastly, what has the model learned? And this is the explainability issue, which I think many of Marzieh's points I agree with. I'm just going to take a slightly different take. I think some of this depends on what exactly is the definition of explainability and interpretability one is using. So, I simplify these things in terms of additional metrics of success in some very simple terms. Trust. Can you trust that a given model is appropriate for a specific patient? Consistency. Is it consistent with what is known, with a corpus of medical knowledge? And lastly, the all and terrible term, explainability. So first, trust. What does trust mean? So trust, simply understanding the failure modes. So as I said, prior work suggests, that these models are evaluated based on standard measures of success, and their averages over, these averages are calculated over a range of different patients that have very different characteristics, and consequently, it's difficult to understand whether a single prediction on a patient can be trusted. So understanding when the model will be misleading is really important. And that's something that my group and I have tried to have thought about and have done some work at. Consistency, I think, is sort of self-explanatory. One can articulate some principles that are well established in the medical sphere, and you can test the model to see if that's the case. In the risk stratification sphere, you could, or even in the imaging sphere, you could give the model as input data in which you know the answer. You're pretty sure of what the answer is in terms of risk or the diagnosis, and see if the model is consistent with those observations. And lastly, explainability also relates to trust. And I think it is in a model that is explainable, that can present explanations using a lexicon that is familiar to the healthcare professional, I think is important. And just to amplify this point a little bit, I want to return to this. There's a paper, I think graduate students in our computer science, I think it's in our advanced machine learning class, someone will correct me if I'm wrong, but I think this is still the case, would read. It's a paper by Zachary Lipton, and it's entitled Mythos of Model Interpretability, and it sort of articulates these different criteria in sort of what makes an explainable model. So it has to be simulatable. For a model to be fully understood, a human should be able to take the input data together with the parameters of the model in a reasonable time step through every calculation required to produce a prediction, a very high bar. It should be decomposable, that each part of the model, each input parameter and calculation admits to an intuitive explanation. I think it's such a high bar, it's not quite clear how it would arrive at such an explanation, especially for many of the highly parameterized models that have had a lot of fanfare in recent years. There's lots of post-hoc interpretability metrics that all have problems: text explanations, visualizations, local saliency maps are big. I think we've already touched on some of these. Now, so methods do exist, in particular these post-hoc methods, to help understand what a deep learning model has actually learned. And you can sort of think about a deep neural network. It has some latent representation. It gets some abstract representation of the data, and then it outputs some clinically meaningful quantity. And so if you view saliency maps, let's say, as one way of providing an explanation of these data, you can go to the computer scientist, and in this case, I have a picture of Alan Turing, and he might, begin by looking at activations of the hidden layers, and saliency maps can help us understand what information is most dispositive. But the translation to the healthcare provider who eventually has to use this model is very foreign. None of this falls in this case, in this clinician's vocabulary. So a common sense approach to model explanations that I think is useful is explanations, because explanations are inherently subjective and can differ from specialty to specialty. And it's challenging to arrive at an objective definition of what constitutes an explanation. So I think one point of consternation is that when you go to a machine learning conference and one wants to write a paper on explainability, typically, at least in the papers that I've seen, they demonstrate its effectiveness by applying it to very different data sets, very different tasks. And overall, they say in each case, provide some sort of explanation. So you get something in general that works over a wide range of tasks, but really is not very good for a particular task. They're really not tuned to a particular. So in a sense, they're really not. It's never clear to me how useful those methods are for specific tasks of interest. So deciding what is explainable is hard, but I think in thinking about it the other way, we know an explanation is bad, right? So what defines a good explanation is difficult to understand, but we know that an explanation has to encompass a discussion where all participants speak the same language. So if one is going to try to explain the Heisenberg uncertainty principle to a Shakespearean scholar, that's a very different discussion than explaining the principle to someone who has had an introductory course in physics, or maybe has seen some quantum mechanics before. So explanations have to invoke concepts that are familiar to the listener, the one that you're trying to explain things to. And I think that is sort of the central principle that I think. And I think, moreover, putting the clinician aside, the healthcare provider aside for a second, because at the end of the day, what's really important is the patient. And if a patient goes to their physician and the physician says, well, I think you should take this medication, it's going to make you live longer. And the patient goes, why? And the physician says, well, because you should take it. It's going to make your hair fall out. It's going to make you lose your teeth. It's, going to make you sedentary. You'll feel like you're sleeping all the time. But why should I take this? And well, this model, this deep learning model says that you should do it. I think the patient would also find that a very unsatisfying explanation. So the ability of deriving such explanations are important, not only from the standpoint of the healthcare provider, but for the patient as well. So just in summary, two central points. ML in healthcare setting involves different metrics of success that are used in other settings, and trust, and all of the points I've spoken to really deal with trust as a central issue that must be considered when designing these models. Oh, I always, at the end of my talks, give just a shout out to my research group who helped me think and work on these issues.
Fantastic.